You see, the world is a crazy place, a very complicated place. If you look at it, you see all kinds of things happening. You see the ocean waves crashing against the rocks. You see the clouds forming and dissolving in the sky, and you see the trees swaying in the wind. It is a mess. It is a jumble of colors and motion and noise, and yet we have this idea, this strange intuition, that underneath all that complexity there are rules. There is a game being played. Imagine that the gods are playing a great game like chess. The game is being played on a board that is infinite in size, so we cannot see the edges, and the pieces are very small, so we cannot see exactly what they are. And the worst part is we do not know the rules of the game. We are just allowed to watch. We are like people sitting in the audience watching this giant chessboard. We see a piece move. We say, aha, if a pawn pushes 2 squares forward, then on the next move it can be captured in passing. We try to guess the rules. This is what we call physics. It is the process of guessing the rules by watching the moves. But here is the thing that really bothers me, the thing that keeps me up at night. The rules we guess, the rules we write down on paper in our notebooks are written in the language of mathematics. We invented mathematics. We made it up. We decided that 1 + 1 = 2. We decided what a triangle is. We invented calculus to deal with changing things. These are concepts that exist in our heads. They are inventions of the human mind, just like the game of chess is an invention. So here is the question. Here is the great mystery. Why does the universe, which does not care about us and does not care about our notebooks, obey the rules of mathematics that we invented? It is a miracle. It is a complete mystery. It is not obvious that it should be this way. You could imagine a universe where things just happen for no reason, where there are no rules, or where the rules change every Tuesday. But that is not our universe. In our universe, if you write down the right equations, if you scribble the right symbols on a napkin, you can predict exactly where a planet will be 1,000 years from now. You can predict how a bridge will hold weight. You can predict how an atom will behave. It is almost as if the universe knows math. Or maybe it is that math is the only language the universe speaks. But wait a minute. That cannot be right either, because we invented the math. Did we invent the universe? No, of course not. So there is a deep connection here, a connection we do not fully understand between the logic of our minds and the logic of nature. Let us go back a bit. Let us look at how this started. Think about the old astronomers, the Babylonians. They were very good at predicting when the moon would rise and when the sun would set. They had tables and charts. They knew that if the moon was here today, it would be there tomorrow. They had a system, but they did not have geometry. They did not have the logic of the Greeks. They just had numbers. They were like the Maya astronomers who could predict eclipses with incredible accuracy, but they did not know that the Earth was a sphere orbiting the sun. They just crunched the numbers. Then came the Greeks. The Greeks loved geometry. They loved axioms. They said, let us start with a few simple truths that everyone agrees on. A straight line is the shortest distance between 2 points. Parallel lines never meet. And from these simple truths, they built a whole structure. They proved theorems. They used pure logic. They did not look at the world. They looked at their minds. They closed their eyes and thought, and they built this beautiful tower of Euclidean geometry. Now, jump forward to Isaac Newton. Newton was a smart fellow. He looked at the moon and he asked a question that nobody had asked before. He asked if the force that pulls the apple to the ground is the same force that keeps the moon in the sky. Now, you might say, well, obviously it is gravity, but it is not obvious. The apple falls down. The moon goes around. They look like 2 completely different motions. One is a straight line crash. The other is a beautiful circle. Newton used mathematics to connect them. He used the geometry of the Greeks, and he invented a new kind of math called calculus to deal with things that change. And he found something incredible. He found that if you assume that the force of gravity gets weaker as you go further away, specifically if it follows an inverse square law, then you can calculate the orbit of the moon. Let me explain what the inverse square law means, because it is important. It means if you go twice as far away, the force is not half as strong, it is 1/4 as strong. If you go 3 times as far away, it is 1/9 as strong. It drops off very fast. It spreads out. Imagine a light bulb. As the light spreads out from the bulb, it covers a bigger and bigger sphere. The surface area of a sphere depends on the square of the distance. So the light gets dimmer by the square of the distance. Gravity behaves exactly the same way. So Newton writes this down. Force equals some constant times the mass of one thing times the mass of the other thing divided by the distance squared. Simple algebra. You learned it in high school, but stop and think about what it means. It means that every object in the universe attracts every other object. It means that right now you are attracting the person sitting next to you. You are attracting the moon. You are attracting a star in the Andromeda galaxy. The force is tiny, but it is there. And the math works. It works perfectly. You can use that simple little equation to navigate a spaceship to Pluto. You can use it to predict the tides. You can use it to weigh the Earth. Why? Why does nature follow a rule that is so simple that we can write it in one line? Why isn't the rule complicated? Why doesn't the force depend on the color of the object or the temperature or the time of day? It doesn't. It just depends on mass and distance. This is the character of physical law. It has a simplicity, a beauty that we can capture with mathematics. But here is the trap. Do not fall into the trap of thinking that the math is the reality. The math is just a description. It is a way of keeping track of the score. Imagine you ask, why do the planets go around the sun? Newton would say because of gravity. But what is gravity? Is it an angel pushing the planet? You could rewrite Newton's laws and say that there are angels pushing the planets towards the sun. And if you ask what are the rules for the angels, you would find that the angels push with a force that is inversely proportional to the square of the distance. The math would be exactly the same. The predictions would be exactly the same. The only difference is that now you have angels in your theory, which you cannot see and cannot detect. So we use Occam's razor and we cut out the angels. We say there is just a force, but then Einstein came along and he changed the game again. He said, wait a minute, this action at a distance is spooky. How does the Earth know where the sun is instantly? If the sun disappeared right now, would the Earth fly off into space immediately? Newton's math said yes. But Einstein said, no, nothing can travel faster than light, not even information, not even gravity. So Einstein had to invent a new picture, a new game. He said, imagine space and time are not just an empty box where things happen. Imagine space and time are a fabric, a flexible material. And when you put a heavy object like the sun on this fabric, it curves. It creates a valley. And when the Earth moves through this fabric, it follows the curve. It thinks it is going in a straight line, but because the space itself is curved, it goes in a circle. Now, this is a very different picture from Newton's force. Newton had invisible strings pulling things. Einstein has curved geometry. It is like an ant walking on the surface of an apple. The ant thinks it is walking straight, but it is actually going around the apple. But guess what? To describe this curved space, Einstein had to use mathematics. He had to use a very fancy kind of geometry called differential geometry, which was invented by mathematicians decades before Einstein was even born. These mathematicians were just playing games with logic. They were wondering what would happen if parallel lines could meet. They were not thinking about gravity. They were not thinking about the universe. They were just exploring the logical possibilities of their own minds. And yet, 50 years later, Einstein picks up their notebook and says, this is exactly what I need to describe the universe. How did the mathematicians know? How did they know that the universe would need non-Euclidean geometry? They didn't. They were just making tools. It is like a guy who invents a screwdriver just because he likes the shape of it, and then 50 years later, someone finds a screw and says, hey, this fits perfectly. It is uncanny. It makes you wonder if the math is discovered or invented. Now, let's get really crazy. Let's go down to the small scale, the quantum scale. This is where things get really weird and where our intuition completely breaks down. If you think you understand quantum mechanics, you don't understand quantum mechanics. Nobody does. I certainly don't. We just know how to calculate. In the world of the very small things do not behave like particles, and they do not behave like waves. They behave like something else entirely. We call them quantum mechanical amplitudes. But I like to think of them as little arrows. Imagine you have a stopwatch, and the hand of the stopwatch turns around and around very fast. Now imagine a particle, say a photon of light, trying to go from a lamp to a mirror and then to your eye. Which path does it take? Does it go in a straight line? Our intuition says, yes, it goes in the straightest line possible, because that is the quickest way. But nature says no. Nature says the photon takes every possible path. It goes to the left, it goes to the right, it goes to the moon and back. It goes to the edge of the universe and back. It takes every single crazy path you can imagine. And for each path, we have a little arrow. The length of the arrow is related to the probability, and the direction of the arrow depends on how long it took to take that path. The stopwatch hand turns as the photon travels, so for a long path, the hand turns many times. For a short path, it turns fewer times. Now here's the magic. To find out what really happens, we have to add up all these little arrows. We put the tail of one arrow to the head of the next one, and we make a long string of arrows. And when we do this, something miraculous happens. For the crazy paths, the long winding paths that go to Mars and back, the arrows point in all different directions. One points up, one points down, one points left, one points right. When you add them all up, they cancel each other out. They amount to zero. They don't matter. But for the paths that are very close to the straight line, the paths that take almost the same amount of time, the arrows all point in roughly the same direction. They line up, they reinforce each other, they add up to a big arrow. So the reason light seems to travel in a straight line is not because it only chooses the straight line, it is because all the other paths cancel themselves out. The straight line is just the path where the arrows line up. This is the principle of least action. It is the idea that nature is lazy. But nature is not really lazy. Nature is actually trying everything at once, and the only thing we see is the result of the interference of all those possibilities. And the math we use to describe this, it involves complex numbers. Numbers with the square root of -1. Now, what is the square root of -1? You cannot have a square of a number be negative. If you take 2 times 2, it is 4. If you take -2 times -2, it is also 4. So what number times itself gives you -1? It does not exist in the real world. You cannot have the square root of -1 apples. It is an imaginary number. We invented it. We made it up to solve certain algebraic equations. And yet this imaginary number is absolutely essential for quantum mechanics. You cannot describe the behavior of an electron without it. The universe runs on imaginary numbers. The universe runs on math that we thought was just a fiction. This brings us to very uncomfortable realization. We are like people looking at a map. We see the lines on the map representing roads and rivers, and the map works. If we follow the lines, we get to our destination. But the lines on the map are not the roads. The map is not the territory. The math is not the universe. There is a problem in our physics today, a deep problem. When we try to calculate things with our fancy quantum theories, sometimes we get answers that are infinite. We ask how much energy is in an electron, and the math says infinity. Now, that is nonsense. You cannot have infinite energy in a tiny particle. So we have to do a little trick. We call it renormalization, but it is really just a shell game. We subtract one infinity from another infinity and hope we get a finite number left over. It sounds like cheating. It sounds like hocus pocus. And in a way it is. We are sweeping the dirt under the rug. But the amazing thing is that after we do this hocus pocus, the numbers we get match the experiments to an incredible precision. I mean, a precision that is equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. So we have this tool, mathematics, which is full of tricks and imaginary numbers and infinities, and yet it describes reality better than anything else we have. Why? I think about the sausage. You know, if you have a sausage and you slice it straight down, you get a circle. If you slice it at an angle, you get an oval. If you slice it lengthways, you get a long strip. The sausage is the reality. The slices are our different views of it. Our math describes the slices. We have equations for circles and ovals and strips, but maybe the universe is the sausage and we are just seeing the slices. In relativity, we talk about space and time mixing together. It is like the sausage. Past, present, and future are all there in the block of the universe, just like the meat is in the sausage. When we move through time, we are just slicing the sausage layer by layer. And depending on how fast we move, we slice it at a different angle. That is why time slows down when you move fast. You're taking a different slice through the four-dimensional sausage of space-time. Again, the math describes this perfectly. The Lorentz transformations tell us exactly how the slice changes angle. But does the math tell us what the sausage is made of? No. It just tells us the shape of the slices. This is the limitation of our knowledge. We know the pattern, but we do not know the substance. We know the rules of the chess game, but we do not know what the board is made of or why the game is being played. And maybe that is okay. Maybe we should not be so arrogant to think we can understand the why. The how is beautiful enough. The fact that we little apes on a small planet orbiting a mediocre star can use our invented symbols to predict the dance of atoms and the collision of galaxies is a triumph. It is the greatest adventure of the human mind. We keep looking for the ultimate law, the one equation that explains everything, the equation that you can put on a t-shirt. Maybe we will find it. Maybe we won't. Maybe nature is like an onion with infinite layers. We peel one layer and we find another layer underneath. We found Newton's layer, then we found Einstein's layer, then we found the quantum layer. Maybe there are gears and wheels inside the electrons. Maybe there are tiny angels pushing things around after all. But whatever lies at the bottom, or if there is no bottom at all, we have this one flashlight to guide us in the dark, mathematics. It is a tool we forged in our own minds, but somehow it fits the lock of the universe. When you look at a rainbow, you see colors. A poet might say it is the bridge to the heavens. A physicist sees the reflection and refraction of light in water droplets. He sees angles and geometry. He sees the math. Does that make the rainbow less beautiful? No. I think it makes it more beautiful. Because not only do you see the colors, but you see the deep underlying structure, the harmony of nature. You see that the same laws that make the rainbow also make the stars shine and make the atoms in your body stick together. You are part of this mathematical structure. You are a bundle of atoms following these strange rules. Your thoughts, your feelings, your memories are all dancing to the tune of these equations. And yet you are conscious. You are aware. You can ask these questions. The universe is a mystery, a glorious, beautiful mystery. And we are the detectives. We may never solve the case completely. We may never catch the culprit. But the chase, oh, the chase is wonderful. The thrill of finding a new clue, a new connection, a new equation that works, that is the prize. So do not be afraid of the math. Do not think of it as boring schoolwork. Think of it as the secret language of nature. Think of it as the music of the spheres. And remember, even though we made up the notes, the melody is real. The melody is out there playing in the silence of space, waiting for us to hear it. Whatever you do, keep asking questions. Keep looking at the world and wondering why. Why does it wiggle like that? Why does it fall like that? And when you find an answer, don't stop. Ask why again. Because the more you ask, the more you see. And what you see is always more fantastic than anything you could have imagined. The world is not what it seems. It is stranger. It is deeper. It is more mathematical and yet more mysterious than we ever dreamed. And that is the way it should be. Because if we knew everything, if we had all the answers, the game would be over. And I, for one, am enjoying the game too much to want it to end.